Okay, good morning. So, as I told you, I will move to the next chapter. This is a very technical chapter. I want you to pay attention to it so you can learn. And then this book, if you remember, the first time that you might have seen complex numbers was in Math 2C. So this book is also assuming that you have already learned those things there. So I will not assume that, so I will start everything from scratch. Today probably I will go through a little bit of history about complex numbers, because might be you have heard about imaginary numbers and things like that. There's, I don't know, sometimes there are some mysteries associated with these numbers, but I just want to remove these things, and I tell you that this is very simple idea if you think in this way. So the first motivation why we actually need complex numbers comes from the fact, actually, the inventor of the complex numbers is called Friedrich Gauss, actually, which is called the king of mathematics, and that is a German mathematician, very brilliant, living in 19th century. And he actually introduced these things in his PhD thesis, actually. And why is that? Because let us look back at the equations. If I give you an equation, for example, 2x minus 4 equals to 0, it's a polynomial equation. What do I mean by that? I mean that you have a polynomial on the left-hand side, and then equality, and you are supposed to solve that equation, yes? If I ask you to solve this equation, of course you tell me that x is equal to 2, and 2 is a natural number, yes? That is the number system that we are aware of naturally, yes? The set of natural numbers is actually starting. For example, let us consider 0 as the natural number in this case. 0, 1, 2, 3, etc., etc. So this is natural for us before technology was advanced, so we only know about these numbers, yes? Okay? And then if I want to solve this equation, the answer that I get is one of the members, so I would say that the set of natural numbers is enough for me to find a solution for this. It means that I can find my answers in this set. But it is clear that this set is not enough if I want to solve all polynomial equations. And that is very simple. For example, if I give you this, so let me write it, plus 4 equals to 0. If you want to solve this, you get minus 2, but minus 2 does not belong to n. So this is why mathematicians actually started extending the system of natural numbers to a bigger one, and that is called the set of integers, which includes the negative ones as well. So you have 0 plus or minus 1 plus or minus 2 plus or minus 3, etc., etc. Okay, but the problem is not finished here, because you can also assume another polynomial equation which has a solution, but it is not in this set. For example, I can say 2x minus 1 equals to 0. Yes? Then what do you get? You get x equals to 1 over 2. 1 over 2 is not in the z. So we have to extend this. Yes? So in order to have the solutions there. And that is why we introduced a set of rational numbers. The set of rational numbers are all fraction numbers, so that a and b are integers, and b is not equal to 0. Yes? But then immediately you realize that this is not also enough. So you see what I am doing? I started from a set n. Let me make it like this, visualize it. It was not enough for this equation. I extend my set to a bigger one, which not only contains everything before, but there are some new elements here, the negative ones, for example. And then I realize that is not enough. I still expand it a little bit more, yes, and then I call it the set of rational numbers. So of course the rational numbers also contain every element in Z, but not all of it, but there are something more. For example, 1 over 2 is in Q, but it is not in Z, so it's really expanded. And this is not enough. For example, if I ask you, what about this equation? This is also a polynomial equation. If I ask you to solve that, then what you get x is plus or minus a square root of 2. But that is probably a known fact for you now, that square root of 2 is not a rational number. So it means that the set of rational numbers is not enough. We have to add something to this and make it bigger. We found the set of real numbers. Yes? So we found a set of real numbers, so it means that it contains all rational elements, but it also contains irrational ones. It's bigger. But the story does not finish here, because I can also have this one. Very simple equation. This equation is a polynomial equation, but you cannot find any number in R that satisfies this. And why is that? Because if I choose x in R, no matter what the value of x squared is at least 1, at least 0. But when I add 1 to it, it becomes definitely greater than or equal to 1 and cannot be equal to 0. Or in other words, so you can write it as x squared minus 1. This is equivalent to this one. But is there any number in R so that when I square it, it becomes negative? No. Okay? And there are two attitudes here. Either you can say that, okay, these equations are not allowed, or you can follow the history of this mathematics and try to extend it one step more. By the way, if you want to see, and then Gauss tried to say that, okay, let us keep, by the way, the rules of algebra here, the way that you add numbers, multiply them, raise them to powers are the same in all of them. So arithmetic is left intact in all of them. So what is happening, I am adding more elements to them, but the rules of arithmetic remain the same. Yes? So then Gauss asked himself, is it possible to do this once more so that it contains the root of this equation as well? Yes? And then he extended that and called it the set of complex numbers. Yes, and then we denote it by this symbol. By adding an imaginary number, which he called it I, so that it squared is negative 1. Yes? So this is just imagining there is a number so that it squares becomes negative 1, and he asked himself, let us add this new rule to all the previous rules that we have so far and explore the consequences of this assumption. So understandable. So you see, do not resist. Still your brain might resist what is I. If I want to give you a feeling, what is square root of 2, by the way? So square root of 2 is very natural for you. Your brain does not resist against it because you have used to working with the square root of 2 all the time. But what is the square root of 2, by the way? So you get a feeling by putting a square root of 2 in the calculator, you get some digital number or decimal points there. But that is not square root of 2. That's an approximation to what we call the square root of 2. Okay, the question is that, what is the square root of 2? I just want you to understand the feeling of resistance. When I say that we have a number whose square is minus 1, you think that this is not possible because your brain has used to working with real numbers, yes? But even in the system of real numbers, if I ask you what the square root of 2 is, what is your answer? The square root of 2 is not the number that you see on the display of your computer or the calculator. So then what is it? Any definition of a square root of 2? The square root of 2 is the number whose square is 2. As simple as that. Yes, it's not mysterious. Exactly. So you see that you were in the same situation when I asked you what is the square root of 2? Square root of 2 is the number whose square is 2. How do we know that such a number exists? Yes, if we accept some axioms, based on those axioms we can show that in this set R, there is a unique number, there is a unique positive number whose square is 2, and then we call it square root of 2, and we denote it by this symbol. Is that understandable? So in the same spirit, you can imagine, let us imagine there is a number I whose square is -1. Exactly like what is the square root of 2? A square root of 2 is a number. By the way, if you go back to Pythagoras, you know that probably by some religious beliefs, they believe that only natural numbers exist, or only rational numbers exists in the world. Yeah. But then Pythagoras was in trouble. Do you know why? Because he himself invented the Pythagoras theorem, yes? And then so you see, he realized that if he has a right angle triangle, 1 unit, then this number becomes the square root of 2. So he realized the square root of 2 is somewhere there, but he didn't want to believe it because it was against his religious beliefs, you know? But he knew about it probably. And then, so the existence of a square root of 2 is actually being forced by having this Pythagoras theorem, yes? So here we also do the same thing. We are assuming that there is a number. Of course, this number cannot be here. So I extend my imagination by making this set bigger and assuming that there is somewhere here, we call it I, for imaginary. That's the reason that people call it I. So that the squares becomes -1. And then the logic is this. The logic is, I want to keep arithmetic so far exactly the same, but I have one new rule to the game, and just want to explore the consequences of this new rule. Yes? It might happen that it is just useless, that I just start a new game, but this game could have been useless or could be useful. But it turns out to be extremely useful. Yes? And this is why people keep it and then start exploring it. What are the consequences of this? For example, if you want to calculate some integrals, which is just the normal way of thinking when we are working with real numbers, there are some integrals that we cannot really calculate. But using the tricks and techniques that is being developed by this idea, we can find some tricks to work those integrals out. Yeah, that's very important, you know. So that's just a mathematical curiosity might be for being able to solve this equation, but the consequences are actually very rich. And this is why people are still investigating and doing research on complex numbers and complex analysis in general. Because it will help us to do something in our real system of numbers. So what I want you to have this in mind. We imagine there is a number whose square is -1. Definitely this number is not in our real system of numbers. So this means that we have to expand it, and so that it includes such imaginary numbers. And then we want to have one thing. We want to keep all arithmetics so far the same. Okay? And see that what new things we can get out from this assumption. We are just inventing a new game, if you want to, and then try to understand this game. But this game turns out to be very useful. Is that right? So that mathematician was living in 19th century. Okay. And then one natural question is that, is it enough for all polynomial equations? Or might be at some point we reach to another polynomial equation whose solution is not inside C, then we have to expand C a little bit bigger to include those. So that's natural question, yes? So you see, in all cases, I am just extending the set to be able to include the roots of different equations. So that is one equation. The solution was not in R, so I extend it to contain I, so that I squared is -1. And if I ask you what is the solution to this, you say I is a solution. But this I does not live in R, lives in C. But this is natural. Is there any other question, any other equation that might be, not now, but in the future, we come across so that its solution is not in C. First of all, I want you to feel that this is a natural question, yes?
Yeah.
But then Gauss himself proved no. This is the end of the story. So you don't, if your goal is to solve polynomial equations, you do not need to extend C to a bigger set of numbers. That is completely enough. So it means that if I give you a polynomial equation, even with a very high degree, and put it equal to 0, all the solutions of that polynomial are among these complex numbers. So that is a very, very big triumph. Yes, so you don't need to extend it anymore. That's the end of the story. Yes, is that clear? That's a little bit of history. But something interesting happened. Of course, he called it imaginary because probably he was imagining it, so I don't know. But in the beginning of the 20th century, that's also something very interesting. People think that this is imaginary, but let me give you a little bit of history. So before 20th century, people working Newtonian mechanics, yes? So Newtonian physics in principle. So the laws of Newton and later Maxwell in electrodynamics was enough to explore, to explain all the phenomena around the human at that time, yes? But then, I don't know, somehow they have started doing that by advancing the technology being more advanced. They realize that there are some deviations that we cannot explain, no matter how hard we are sitting and doing the experiment. So let us consider classical mechanics. So the formula for classical mechanics is something like this. And if you want to write it in a little bit more advanced form, m is the mass of the particle, and then this one is the second derivative of your position. So let me just consider one-dimensional case. You have a particle of mass m moving around under the influence of such a force. And then this is the Newton's law, yes? So in principle, if I give you the initial condition of this particle, meaning the initial position and initial velocity, and I give you all the forces acting on this particle, using this differential equation, you are able to predict the future positions of this particle. That is the main thing that we do, okay? But the point is that if I take this mass and consider an electron instead of this big mass, fairly big mass, this is a macroscopic mass, but assume that we have an electron instead. If you use this, you cannot predict the behavior of the electron. So in principle, people was thinking that, okay, electron is also something, is like a mass, but a very, very tiny mass. But in principle, they think that, okay, if I give you all forces acting on the electron, and then you use the Newton's second law, you can predict the behavior of the electron. Okay? But it turns out that this is much harder. So whatever you calculate on paper, and when you go and do the experiment, you do not see, you see discrepancies all the time. So what you write on the paper to predict the behavior of the electron, and when you go to the lab and do the real test, you see that there is very, very big deviations from those results. Okay, and then I don't know, that was a very big challenge for humanity at that time, and then finally Schrödinger changed this fundamental equation to another equation that is famous to the Schrödinger equation. And it's also a differential equation, but that's a partial differential equation. It's a little bit harder. I want to write the mathematics here, but I don't want you to be involved here, so that's much. So let me write, h bar is Planck constant probably, divided by 2 pi. You have seen Planck constant probably in physics work, but that's just fundamental constant of nature, like the speed of light. And then this is the derivative, written a little bit strange, and this psi is a Greek letter. So don't get involved with these things. So let me just write this. I don't know. For example, the potential function times psi itself. So that is the Schrödinger equation. This is just d. But this psi is a function of 2 variables, so we have this. This is t, I don't know, this is the mass, this is the potential energy for the electron. And the point is that if you use this equation to predict the behavior of electron, again you get the wrong answers. Unless It's very strange, unless you put this I, who Gauss invented in 19th century. Okay, so if, I don't know, this is the equation governing the electron behavior. And of course, if electron is not imaginary, it is in our universe, then probably if you take this I, who this guy invented there, away from this equation, again you will get a lot of discrepancies. You cannot predict the behavior of the electron. But as soon as you put I there with a lot of interpretation, then you can predict the right behavior of the electron. Okay, and then this turns out to be the fundamental equation for our nature if quantum mechanics is right. But if, I don't know, that is up to you to decide if I is imaginary or not. Because if you remove I, the predictions are not correct. But if you put I there, the predictions are according to experiments. They are correct, yes. So in some sense, it is not imaginary. But on the other hand, it is imaginary. Why? The point is that if you go to the lab and do some experiments, the numbers that you are get at the end are all real numbers. If I measure the position, if I measure the momentum, electric charge, or whatever related to an electron, I will never ever get a complex number, including I. So the results of measurements are all real numbers. But if you take this I away from the fundamental equation, you get the wrong answer. But if you put that I, you get the correct behavior. Then that's up to you to judge. Of course, Gauss was not actually even aware of these consequences. So that is some piece of history. If you ask the right question and try to explore its consequences, the consequences probably are much more rich than even you can imagine yourself. Yes? But anyway, that is up to you to decide if I is imaginary or real in our universe. But I just told you that if you take I away, this will not work. If you put I, it will work. But another point is there is a big difference still between real numbers and complex numbers, in the sense that if you do measurements and get numbers, those numbers are all real numbers, not imaginary numbers. Yes? That is just a piece of history that you get understand it. So do not resist about this symbol. So the logic behind this is this. We are adding a new rule to the game of arithmetics that we have so far, and we try to explore its consequences. Yes, the reason that still we are studying in 21st century this is because it has proven itself over and over to be useful. Yes? That is, by the way, in mathematics. In mathematics, you can imagine whatever you want. The only thing that mathematicians care about consistencies. If there is an inconsistency in your mathematical system, then you have to throw it away, definitely. But if it works, then there is a question. Is it useful mathematics or not useful mathematics? That is up to you to decide, or about the application. But in physics, we not only have axioms, but the axioms that we assume, the rules that we assume, should be compatible with what we see in the experiments. Yes, so that is something that mathematicians usually doesn't care. But of course, they have shown that their intuition and attitude toward mathematics is really useful. Because if, I don't know, if he hasn't invented this number there, I don't know if Schrödinger were able to find that here right away. Yes, I don't know. So that is important to understand. Okay, so don't get confused. I am trying to teach you the consequences of this assumption on top of all arithmetics we have so far for R. Yes? Is that clear? Okay, so now we start formally introducing you a complex number. So this is not in the book. It's assumed that you already know these things in Math 2C, but I told you I will not assume that. I will start from scratch. So the first thing is the definition. So let me start with definition, yes? A number let me write it like this. A plus b I, where a and b are real numbers and I squared is minus 1 is called a complex number. Okay? The terminologies I want you to know. I is called, let me write them here. I, what is the name for I is called the imaginary unit. The reason that we call it unit we will see later. The imaginary unit. Okay. A, this number comes first without any i's, is called the real part. A is called the real part, and then B, not including I. B itself is called the imaginary part. B is called the imaginary part. Yes? So remember these words, yes? Imaginary unit, the real part, the imaginary part. And there are some symbols for that. It is common that we denote complex numbers by letters Z or W. This is very common, okay? So when I say that I have a complex number Z, what you expect to see is a number, a real number, plus another real number multiplied by that imaginary unit I, which follows this property, yes? I squared is negative 1. And then A is called the real part, and the symbol used is RE of Z, and we call it real part. And B is IM with capital I, Z. So it is extremely important, do not get confused. When I ask you the imaginary part, I have seen some students say BI. No, only the B part is the imaginary part by definition, yes? So these are the things and the symbols that I want you to learn. Okay? So now, for example, if I give you Z, number 1, for example, 2 plus 3i, this is a complex number. Yes? And then what is the real part of Z1 is 2. What is the imaginary part of Z1 is just 3, not 3i. And then, for example, if I give you another complex number, number 2, so let me just write minus 1 plus square root of 5 divided by 2i. That's also a complex number. Because, by the way, remember this form. This is called the standard form. Standard, or sometimes Cartesian form. The reason that we call it Cartesian is it becomes clear when we progress in the course, in this topic. So, the standard or Cartesian form of the complex number. Okay, so this is also a complex number. If I ask you what is the real part, it's negative 1. If I ask you what is the imaginary part, the answer is a square root of 5 divided by 2. Yes? For example, what about this one? Just I itself. What is the real part? Because I, you should imagine, I is what? 0 plus 1 times I, yes? Why this is correct? I told you that because I want to keep all the rules of arithmetic the same. Yes? So if the rules of arithmetic are the same, you know that any number multiplied by 1 should be the number itself, so that becomes I, and every number plus 0 should be the same number. That is the logic. I want to keep the arithmetic the same. Okay, so this means that you can immediately tell me what is the real part now. What is the real part? 0. What is the imaginary part? What is the imaginary part? Sorry. Is 1. And let me answer this question as well. That's also good to know. Just write -5, for example. Is this also a complex number? From that picture that I told you, you should say yes, because -5 is a real number, and I told you that the set of complex numbers in principle should contain all the real numbers with some extra numbers. So from that perspective, you expect the answer to this is yes. On the other hand, you can also use it the arithmetic. You want to keep the rules of arithmetic the same, so I am allowed to write this. If someone asks you why, because I would say that 0 multiplied by any real number before was 0, so I want to keep the arithmetic the same, so the answer to this is also 0, and if I add 0 to -5, it becomes -5. But now, what is the real part here? What is the real part of Z4? Is -5, and what is the imaginary part? Is 0. Yes? So in that case, is it correct to say that every real number is automatically a complex number? Yes. Yes, but not the other way around. So this complex number is not within the complex, is not in the real system. It's just in the complex numbers. But this one is correct. So in that case, in the language of set theory, we can say that R is a subset of the complex numbers. So whatever is in R is already in C, but not the other way around. There are some other terminologies that I want to use. A number whose real part is 0 is called pure imaginary. I saw that is also in your book. So if Z, a complex number Z, is called a pure imaginary. These are just terminologies, yes? Complex number, if a real part, real part of Z is 0. We can also have pure real, but we just call it real. Yes, pure real means that its imaginary part is 0. But we don't say pure real, we just say real. So that is just the terminology I want you to know, pure imaginary. What do you think will play the role of 0 here? What is 0? B. Is it a pure imaginary number or not? First of all, 0 is real. Is it also pure imaginary? Yes, because its real part is also 0. Yes, so 0 is just an exception. So 0 is 0 plus 0i.
So it's both.
Yeah, so the both real part and the imaginary part is 0. So it is a real number because 0 is a real number. It's also a pure imaginary number because its real part is also 0. Yes? So 0 is just 0 plus 0. So it means the real part of 0 is equal to its 0. Imaginary part of 0. Both are 0. So we don't bother to write 0 plus 0i, we just simply write 0. Okay? Any questions? Yes or no? Okay. So let us, before going further, explore a little bit of nice relations just for I. So we know that I squared is -1. Why? By its definition, by its imagination. But what if I ask you what is I3? I to the 3. What is that one then? So let us just explore this. Yeah? So what happens if I want to calculate I to the power of 3? I told you that I want to keep the arithmetic the same. So if the arithmetic is the same, I am allowed to write it like this. Agree with me? Because that is one rule of arithmetic for real numbers. I told you that I want to keep the arithmetic the same. So in the complex numbers, this should also be correct. Yes? Or I demand it to be correct. And then I squared is something is minus 1. So that's minus I. So I to the 3 is minus I. Okay? And it is extremely important, by the way, whenever I squared appears in the questions, you have to replace it with minus 1. Of course, you can leave it. Technically, it is not wrong, but you need to show that you respect and you know I squared is minus 1. So you have to write minus 1 instead. Okay, so for example, if I ask you what is I to the power of 51, what's the answer? Simplify this as much as possible. I to the power of 51. There is only one definition that you can rely on, and that is I squared is minus 1. So what should I write?
I to the power of 52 times I.
Yeah, I to the power of 2 to the power of 25 times I. Do you agree? Because I to the power of 2 to the power of 25 becomes I to the power of 50, and I to the power of 50 multiplied by an extra I becomes I to the power of 51. Why this is true? Because I told you I want to keep the arithmetic the same. But I squared is what? Is minus 1. So you write minus 1 to the power of 25, and then you multiply it by an extra I. But you know this answer from your previous arithmetic knowledge. What is that? Minus 1, because this is E odd. And then it becomes minus I again. So I to the power of 51 is minus I. Yes? Okay, so for example, 1 over I is a very nice relation. It's minus I. So this is one of the consequences that you have to admit and you have to live with it. Yes? Because in normal calculus, in normal real numbers, if I have this, it becomes 2 to the power of minus 1. Yes? So you expect to put the minus sign up there. But here, it is not wrong to write this. Why? Because I told you that I want to keep all the rules the same. So if you write this, that is true, but something more is true, which was not true in the beginning. So if I write 1 over 2, so I can compare the unit with the number 1. If I write 1 over 1 is 1 to the power of minus 1, that is correct. But if I write 1 over 1 is negative 1, it is obviously wrong. So you see that when I add something to the game, there are some consequences that you cannot expect before, that are happening before, that there are something new happening. So this is still true, because I demand the arithmetic remains the same, but this is of course in this case wrong, but in this case is still true. Can you tell me why? Why 1 over I should be minus I? It's very simple, yes? What is I squared? I squared is minus 1. Yes? I squared means I times I. Yes? I times I. Why? Because arithmetic is remained the same. But can I divide by I, both sides?
Oh, yeah.
Yes or no?
Yes.
Why we can divide? I have to make sure that what I am dividing by is not 0. But is I equal to 0? No. By the way, we have to define what do I mean by equality of complex numbers. We will define that. But we know that I is not equal to 0. I can divide everything by I. But the arithmetic, I demanded to remain the same, so I can cancel it out. And then it becomes I equals to minus 1 over I. I multiply by a negative sign, it becomes that. Yes? So 1 over I is minus I. Yes? So this is something we have to accept. If we accept that I squared is minus 1, this is an immediate consequence of that rule. Yes? Okay. Any questions here? So there are very interesting things that can happen, okay, but before doing that, you see that I have to define what I mean by two complex numbers to be equal. So if you are the mathematician and you want to define it yourself, you are free to define it in any way, unless you are inconsistent. But what is the most natural way of defining two complex numbers are equal? When do you think I give you two complex numbers, and I say these two complex numbers are equal if what happens? What is the most natural way to define equality of two complex numbers? Yes?
If A and B are the same.
No. A and B?
A.
No, I am asking you what is the...
A is equal to C and B is equal to D.
to D. That is the most natural one. So you are saying that two complex numbers are said to be equal if the real parts are the same and the imaginary parts are also the same. Yes? So this is the definition. So we say that A plus BI is equal to C plus DI if and only if it means equivalent to saying that A is equal to C and B is equal to D. That is important to know. So equality of two complex numbers provides you two pieces of information. It gives you two equalities. Yes. For example, let me give you an example using this idea. So example, it's a very simple one. So I would say that let x and y be real numbers. So let me write it in this way. Determine real numbers x and y. X and y such that x plus 2y plus I times x is equal to x minus x, let me write 4y plus 2x minus 1 times I. Yeah, it's a very simple question. So you see, I have given you two complex numbers, one on the left, one on the right. I have emphasized that x and y themselves are real. Because be careful, when I say standard form of a complex number, a and b has to be real. Of course, it doesn't mean that a and b cannot be complex themselves, but that is not a standard form. I will talk about that later. But here, is this the standard form of my complex number? Yes. The whole package here is the real part, and this x is the imaginary part. On the right-hand side, this part is the real part, and that part is the imaginary part. So then what happens, if these two numbers are supposed to be equal, this happens if and only if the real parts match, and is this curly bracket, and the imaginary parts also match. Okay, then it is easy to solve this system. This becomes 1, and then you put it here. 1 plus 2y is 4y. Then it means that y is 1/2. Yes? And that's the answer to this problem. So remember, two complex numbers are equal if and only if the real parts are the same and the imaginary parts the same. Okay, what comes next? So you introduced an imaginary unit with some, for the time being, odd property, but the logic is clear. We want to keep the arithmetic and explore the consequences. Now we go one step forward. So what is the next step, do you think I should do? So now you know what a complex number is, just by definition, not imagination, yes? But then, the next step, is to tell you how to do the arithmetic on this new set. Meaning, how can I add the numbers? How can I multiply them? How can I divide them? How can I raise them to powers? Everything. Taking the square roots, taking the third roots. All these things that we have learned so far for real numbers, in principle, I should be able to answer for this set. But I want you to understand it yourself. So, you want to define, so tell me this. A plus bi is a complex number. I want to define how to add this complex number to this complex number. Of course, in principle, you can define whatever you like as far as you are consistent, but the most natural definition is what? So what is the natural definition here? If I want to add these two complex numbers, well, how do you define the addition? Yes?
It feels like you should add A and C and B.
Yes, separately. Because I told you that I want to keep the arithmetic the same. So this, I will take it as A plus C. And then you know that in the normal arithmetic, so compare it with this combination. In the normal algebra, am I allowed to factor x out? Yes. But here, I want to keep the algebra the same. So now instead, I can view that I is playing the role of that x. If I could factor x out in the real algebra, in principle, I should be able to factor I in the complex algebra. So that is what you define is completely correct. So then I will add b and d to I. Yes? And the next thing is a plus bi, the difference between two complex numbers, and that it turns out to be the same. So if you don't mind, let me put a pair of brackets here, even though it is not necessary. And this time it is very simple to convince yourself that this is the case. Yes? But now this I want to describe is actually very good to understand what is going on. But mathematicians actually define the product is a little bit unusual. So C plus DI, they define if you want to multiply these two complex numbers, do this. What? Do A multiplied by C minus B times D, and then write A times D plus B times CI. Okay, so that is the way that you have to multiply two complex numbers. It seems strange. So if you want to multiply two complex numbers, take the real part of this one, multiply by the real part, multiply the imaginary parts and subtract them, and then multiply the real part by the imaginary part, multiply the imaginary part by the real part, we start add them. Yes? It might seem that this is a very strange way of defining the product. But it is not strange because you are supposed to keep the algebra and arithmetic the same. If you insist to keep the algebra the same, that is the natural consequence of that. Let us explore it. I mean, that is the only way that you can define the product, the multiplication operation, if you want to keep whatever you have so far intact. Why is that true? Because if I want to multiply A plus BI as just normal numbers, so it means that I have to have the distributive law. Because in real numbers I could distribute, I want to keep the rules the same, so in complex numbers I also should be able to distribute. So this means that this becomes AC plus ADI, and then this is BC I plus BDI squared. You cannot just rule this out because I want to keep the algebra the same. If I want to keep the algebra the same, this should be right. But then you have to admit, because of the definition, that is minus 1. And then what happens? You get AC minus BD. And then because you want to keep the algebra, you are able to factor the I out. And that is exactly how they define it there. Yes? So, you see, this is apparently a definition, but that is the natural consequence of keeping the algebra the same. Yes? Okay, for division, it is much more unusual. I don't even remember it myself, yes? So, if I want to do that, so the answer to this, because you know that, first of all, what do you expect? When you add two complex numbers, the answer is again a complex number. When you subtract two complex numbers, the answer is a complex number. When you multiply, the answer is a complex number. So when you divide, you also expect to get a complex number. A complex number means a real part plus an imaginary part. That is the meaning of complex numbers. Yes? So you should have it in this form, but a plus bi divided by c plus di is not that natural. Let me see if I can reproduce it in my head. C squared plus d squared in the bottom, and here you have c squared plus d squared in the bottom, I. And then you change d, so this becomes ac plus bd, and then it becomes bc minus ad. It's unusual. Yes. So if you want to divide two complex numbers, it's really strange. Yes. You have to write c squared plus d squared in the denominators, and then you have to write a times c plus b times d, and then write b times c minus a times d, or whatever. Yes? But I myself do not have it in my memory, I just reproduce it. So in principle, you can define these things. Okay? You can define these things, but these definitions are forced upon you because you want to keep the algebra the same. About this one, I described how, but what do you think about this one? I want you to learn this, because if you just memorize the formula, first of all, this formula is not in the formula sheet, and then memorizing it will not bring you any points. You need to learn how to motivate this. Okay, but I want to teach you here. So a plus bi divided by c plus di. Yes? This is what you need to learn. Whenever you want to divide complex numbers, you have to rewrite the complex number as it is, this fraction, and rescale it. Rescale it by the conjugate of the denominator. Okay? And that is the reason why it's clear. I will tell you why. So it becomes c minus di, c minus di. This is a valid argument. Why? Because I want to keep the algebra the same, so I know that if I divide a number by itself, it's supposed to be 1, because I want to keep the algebra the same. And when I multiply 1 by a fraction, it becomes the same fraction, because I want to keep the algebra the same. But now let us see what happens. In the numerator, I just multiply according to multiplication rule. But it is hard to remember these formulas, so this is why I always do it. So I multiply a by c, a by minus d, I, and then I have bci, and then I have minus bdi squared. But don't, even though you can multiply here, but don't do that. Use the conjugate pattern, it is easier. This becomes the first one squared minus the second one squared, yes? Because I told you that I want to keep the algebra the same, so it will work here as well, yes? And then let us see how it goes. This I squared here should be replaced by minus 1. So it gives me positive BD. I add it here. It becomes AC plus BD. And between these two, I can factor an I out. BC and minus AD are left. But what happens for the denominator? C squared is C squared. This is minus. This becomes d squared, I squared. Yes? But I squared is again negative 1. So this becomes c squared plus d squared. So this becomes ac plus bd plus bc minus ad times I divided by c squared plus d squared. And then I divide this by that because I want to keep the algebra the same. And then plus bc minus ad divided by c squared plus d squared I. And that's the formula that I have written here. So you see that even though this is a definition, but definition is a natural consequence of this assumption that I want to keep the algebra the same. And I want you to, every time I give you a division in the exam, you have to do this process. You are not allowed to use the formula. Okay? Is that clear? Okay, so something that I want to mention here, can you tell me what is happening? If I give you two complex numbers, let me call one of them Z, another one W. Can you write a nice relation here for me for the real part of Z plus W? It's on the board, yes. If I ask you what is, so let me call this number Z, let me call this number W. I ask you what is the real part of Z plus W. You add Z to W, you get this one. What is the real part? The real part is this. This is the real part of the sum. Do you agree? So the answer is A plus C. But what is A? A is the real part of Z. What is C? C is the real part of W. So you can write the real part of Z plus W is equal to the real part of Z plus the real part of W. These are spread around in the exercises, but these are very simple. I want you to understand them. So the real part of Z plus W is the real part of Z plus the real part of W. Yes? And if I want to write Z, the real part of Z minus W, so by the way, I can also write the imaginary part. Do you agree? The imaginary part of Z plus W is this part. But this D is the imaginary part of Z, this D is imaginary part of W, so this becomes imaginary part of Z plus imaginary part of W. Yes? But, for example, for this is a little bit more complicated. You see, can I write this relation? Do you agree with me or not? Z times W is equal to the real part of Z multiplied by the real part of W. Do you think this is correct? The real part of the sum was the sum of the real parts. But do you think the real part of the product is the product of the real parts? Apparently no, yes? You see, if I ask you what is this is the product. What is the real part of the product is this combination. But this combination is not this multiplied by that. This multiplied by that appears here, but you have an extra term. So if you want to complete it, the answer becomes minus B times D. B is the imaginary part. D is imaginary part of this. So be careful. So you need to do not invent formulas unless you know. These are not the formulas that you need to memorize, but I want you to understand the notation. So is what I have written in this box is clear for everyone? Using the formula that I have written it here like this. The real part of the product, this is the product, this is the real part. So the real part of the product means this is equal to A, which is the real part of Z, times C, which is the real part of W, minus B times D. B is the imaginary part of Z times imaginary part of W. Yes? Okay, as an exercise, I would recommend you to write a formula similar to these. It's a little bit more complicated, but that's good to be able to do that. That's just an exercise. Okay, so in principle, you do not have any one of these formulas in the formula sheet. Whenever you want to add, subtract, multiply, divide, you have to do everything from scratch all the time. And that is better, by the way, because these formulas are confusing sometimes. Okay, it's always better. The only thing that you have to be careful is about the division. And this rule you need to remember all the time. If you want to divide two complex numbers, write the fraction and multiply it by the conjugate of the denominator. Okay? In that case, you will be able to, and then you start multiplying just as normal and do the calculations. At the end, you just write the numbers. I want to give you numerical examples now. We have a little bit of time, so let me just give you one example and then we'll finish. This is more or less what you need to know from the previous Math 2C studies, okay? Of course, I presented in a way that now you are grown-ups, so you didn't have those kinds of formulas in this way. But anyway, now you understand that. Okay, so now let us just do a very, very simple exercise. And this is crucial. You have to be very comfortable with doing these calculations. So, let me give you two complex numbers. For example, let me give you z equals to 2 plus 3i. And let me give you w to be minus 5 plus I. Okay? If I ask you what is z plus w, very, very simple task. What is the answer? You add the real part, it becomes minus 3. You add the imaginary parts, it becomes 4i. Very simple. If I ask you to subtract them, so let me write them in front of your eyes. I want to subtract them. For this, I really don't need any pair of brackets, so it becomes 2 plus 3i. But here I have to remove it, but this minus sign goes for minus 5 and I. So the first one becomes positive, the second one becomes negative. And then 2 plus 5 becomes 7, 3i minus I becomes 2i. That's the difference. If I ask you to multiply them, you shouldn't use the formula. By the way, it's better to not use the formula, it's easier. You just start multiplying, like if they are polynomials. So you multiply, it becomes minus 10 plus 2i minus 15i, and then plus 3i squared. You have to show respect for I squared when it appears. Higher powers of I should be simplified. Okay? This is minus 1. Minus 1 times 3 is minus 3. Minus 3 minus 10 is minus 13. And then 2i minus 15i is minus 13i. That's your answer. Yes? For example, if I ask you to divide z by w. So this is probably the new thing for you. This is not in Math 2C. And I don't know why they haven't repeated it here. Anyway, so this is 2 plus 3i. I divide it by minus 5 plus I. But this you need to know the rule. What I have to do, I have to rescale it a fraction by what is the conjugate pattern of the denominator. Minus 5, but I have plus I would write minus I. And then I divide by the same thing. That's the only thing that you need to do. And then you have to do two multiplications. Multiplication in the numerator is as before. 2 times minus 5 is minus 10. 2 times minus I is minus 2i. 3i times that is minus 15i. And then this one you can do it by the way in your head. 3i times minus, let me write, minus 3i squared. In the denominator, you can also start multiplying, but do not do that. Get used to working with identities. This is the conjugate rule. If you are not happy with that, you can just multiply as before, but it is better not to do it. So it becomes the first one squared, always and always minus the second one squared. Okay, and then simplify. So this becomes I squared is minus 1. So it becomes positive 3, minus 10 is negative 7, minus 2i minus 15i is minus 17i, and then 25, I squared is minus 1, another minus sign here is 1. So you write minus 7 minus 17i divided by 26, but that is not good. Because usually you should write it in the form of a complex number. A complex number is not of this form. You have to write it in this way. Minus 7 divided by 26 minus 17 divided by 26 and then I. Yes? That is what you have to write when I divide. they can ask you a different question. For example, they can give you z and they can give you w. Instead of asking for z over w, they can ask for finding the imaginary part of z over w. They can ask for this. It doesn't mean that you need to know those complicated formulas. No, not at all. You just calculate zw and put it in the standard or Cartesian form, and then just read the imaginary part of the result. So what is the answer to this question mark? I did the division in full details. I got this, and then I answered this question. What is the answer? Minus 17 over 26. So whenever you are supposed to find the real and imaginary parts of some multiplications or divisions or whatever, first you have to do the arithmetic and put your result in the standard form, and then read the real and complex parts. So don't forget about this. Yes, is that clear? Okay, for example, sometimes they give you letters. Sometimes they ask you, for example, what do you think is this one? How can I calculate I times I plus 1 to power 2? Because sometimes they ask you to simplify this. Or they can ask you what is the real part of this. Or they can ask what is the imaginary part. In all the cases, you have to do the arithmetic until the end and then answer the question. So how should I do that? In the normal algebra, you know that you have to expand this first. Here is the same. So you keep I, and then you raise it to power 2. All the rules are the same, so this becomes the first one squared, 2 times the first one times the second one, and the second one squared. Yes? But you have to show respect for I squared. So I squared is what? Minus 1, and then fortunately this minus 1 cancel that minus 1. So this becomes I times 2I. But then it becomes 2I squared, but I squared is again minus 1, so it's minus 2. So it's very interesting. You see, you start with a complex number, but the answer is a real number. Yes? So if I ask you, for example, assume that I give you this in the exam, but I don't ask you to calculate this, I ask you to calculate this. So what's the answer to this now? What's the answer to this? If I ask you this, you have to do this. Yes? You have to do everything up to there and then answer this question. So what's the answer here? What is the imaginary part of the final result? 0, yes? What is the real part? Minus 2. Yes? So now, for example, yeah, there are some things that are simple to do. For example, what happens if I ask you this question? So 1 plus I to the power of 101. So one way to look at this problem is Math 5 binomial theorem. But that is completely... so how many terms are involved? 102 terms. Yes? So if I give you 1 plus x in real numbers and I ask you to do it, there is only one way. Use the binomial theorem. Yes? But now for this particular case, I can do it simpler. Can you tell me how should I do it? So you need to get some experience in these kinds of calculations. Because if I give you this in the real system, there is only one way. Either multiply it 101 times, or you use the binomial theorem that we learned in the Math 5 lesson. But in this case, if you, for example, this is not always working, so this is why it is interesting. There are new puzzles for you, yes? And then I write it like this, and then I write it like this. First of all, do you agree with this? What I have written is exactly equal to this. What is the benefit of doing this? Because this turns out to be simple. Why? This becomes the first one squared, 2 times the first one times the second one, and the second one squared. And then to the power of 50, and then 1 plus I. But I squared is negative 1, and 1 are cancelled. So what is left is 2I to the power of 50 multiplied by 1 plus I. But this is simple because this becomes 2 to the power of 50. It's a huge number, but who cares? I to the power of 50 times 1 plus I. But can you tell me what is I to the power of 50? Can I simplify it? So how? You need to write by 2, yes? So 2 to the power of 50, I to the power of 2 to the power of 25, and then I have 1 plus I. But I squared is what? Minus 1 to the power of 25 is minus 1. So this becomes minus 2 to the power of 50 times 1 plus I. So then you multiply in. So it becomes minus 2 to the power of 50 minus 2 to the power of 50 times I. That is your answer. Okay? So the good point of this question was to ask this. I could have given you this in the beginning and I ask you, for example, what is the imaginary part of this? These kinds of questions are more popular in exams. I give you this. I ask you this question. If I have asked you this question, everything that I have done here you have to do. But the only thing is that finally you read the imaginary part. So what's the answer to the question mark now according to my calculations? What's that? What is this? Minus 2 to the power of 50. Yes? So sometimes, so you need to get used to this kind of algebra. Yes? So always be careful that if higher powers higher than 2 of I appear, it is always possible to simplify them. Yes? So this is something that you should have in the back of your head. Okay, so this is more or less what I expect you to know from Math 2C. I will stop here, then I will continue this lesson afterwards. So that is actually becomes a little bit tricky and technical, sometimes hard. So please come with me and do not postpone it for later. Yes? Any questions here? Okay, thank you.